Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
On this campus, there's a strong interest in looking at new materials for harvesting photons. We have a number of centers now looking at new materials to actually capture photons and then transport that energy of photon energy into some kind of real electrical energy to some trap, and then creating electrical kinds of currents. And so the gold standard, of course, is silicon. Of course, all the other alternatives of energy have been discussed. I guess there have been some Saturday morning talks already this semester on these materials. And it's very exciting, you know. I mean, to be in this particular edge of research and interest in which your focus of your work kind of fits something that's not only of great interest scientifically, but could have some impact, finally, right? And have some impact that you could see maybe in your lifespan. And so silicon is the gold standard of what people were using for these kinds of solar type applications. And there's a great amount of futility to actually use solar energy, because solar energy is a very important aspect of our daily life. And you can see that the Earth has this abundance of energy that we are allotted from the sun, and it deposits about 120,000 terawatts of energy every year, of which we use hardly nothing. I mean, I guess you could say we use almost in the noise, right? And so this is the real selling point for solar, and that you need to find new materials that are low in cost. So when you hear this talk, this is a different kind of talk for me, because it's actually, and maybe it's something of interest to a broader spectrum of people, that you're not only worried about the details of the physics, but you're also worried about the details of the materials and their actual practical use, right? We actually know of some materials that are excellent solar absorbing materials, but the cost is astronomical. And so it's not really a practical thing to talk about, right? And so we also know some materials that can absorb a huge amount of energy, but they are very heavy. Actually, the fabrication of their devices are extremely expensive as well. And they're not flexible, and then you can't make a large area, or you can't make a lot of them. And so people started to look at other kinds of materials that had those qualities, that they could be made cheaply, that they could be made in a way that you could actually spread them over a large area. Okay, you could make like square footage of these materials and then transport them on a truck or something, right? You could also make them such that they could be flexible if you wanted to, all right? And their efficiencies were starting to compete with silicon. And so we had been doing a lot of work on looking at these materials, in particular looking at their efficiencies and understanding their physics. And these materials became known as these organic light harvesting materials, okay? And I'm actually just going to show these in a broad sense to begin with. For example, these ring-like structures on the left, these molecules, they turned out to be good mainly because of that spectrum right in the middle. It said that they could absorb most of the visible and near IR parts of the solar spectrum. And so people were very interested then in these kinds of materials just because of the absorbing part. But that's the first part. You absorb and you collect the energy. That was the first part. And we were mainly interested, I'm going to skip right to this one. We were mainly interested at the beginning in the absorption and collection part of the energy. And people would make some very simple devices. The devices would be that you would collect the light, the energy. I'm going to do this from the computer. You would collect the light and the energy from the bottom here, okay, and then transport it through some whole transporting layers, and then put it in series with some kind of voltage connector and collect the electricity out of it, okay, like a solar cell. And this is all the beginning part, right? You collecting and harvesting photon energy. Lots of interest in that still, and a lot of research has been done in that. And we were mainly in that area to begin with. But however, while the harvesting part of photon energy is extremely important, the storage part is equally now as important, okay? Those are two different things. So the thing on the top of your roof, the silicon and so on, that's going to harvest the photon energy, make electricity, and do something inside the house. But then you may not need all that energy right this second. You need some way to store that energy, right, until you really need it later. And I'm going to talk about that. Well, is that really important? Well, this is a diagram that I took from the World Energy Council. And they claim, to actually be able to look at this huge problem of energy from a number of different perspectives. One is from the microeconomic or risk perspective. I guess that sounds like what it says. Economically, it may not be such a good investment to go into certain energy resources, and some may be a better investment than others. Geopolitics, energy geopolitics, is a huge one, obviously. So, there is a reason why we still use a lot of petroleum, even though most people say that we should not. And then energy business environment, that's again, and then energy vision. I would say the scientists are kind of down at the bottom about the energy vision, right? We are actually kind of pie in the sky. We're looking for new ideas and so on. But the way to look at this map, I think it's actually a little bit complicated map to look at, but I think it's actually really an important one, is that to the right, you can see, is impact, okay? So as you move to the right of this graph, it's saying you have larger impact. But impact, as we learn in the university research laboratory, and as you learn in your daily life, as well as people learn when they try to translate research into technology and technology into real businesses, has a degree of uncertainty or risk associated with it, right? And so as you move up this graph, you're increasing the risk, you're increasing the uncertainty. And so like nuclear is at the top of this graph, right? But the impact it could have is immense, right? And so everybody agrees with that. We didn't need this committee to decide on that one. But look what's right in the middle, which is a good investment, right? Something in the middle is a good investment. And so things like smart storage, energy, sustainable energy storage. And so I think this is kind of a good one because it has all the colors in that middle there. It has from an economic standpoint, storage rather than harvesting. Storage, right, is a good investment. Energy politics, politically, there's not going to be any politics over storage, right? And then business environment, that was a joke. And then energy vision, right? And so, anyways, this is just to show that don't take my word for it. I presume that the Energy World Council knows that in the future, energy storage is a major factor. So, I do ultra-fast spectroscopy. We have very sophisticated equipment in my lab. We do very fancy lasers and so on. And so this talk really is about capacitors. And capacitors are pretty simple ideas, aren't they? I thought so. And so, but actually they've been around for a while, and I wanted to show this. This picture is a portrait of Mary Shelley. It's like in the 1700s or something, right? And this is a picture that was taken from an experiment done. This was like 2010 about how a great capacitor actually is the actual rainstorm inside a storm, right? Okay, where's the rain and the earth. And this is this romantic idea that science fiction was this idea that you could ever harvest energy large enough that was comparable to what you would see in what is known as lightning. And so this was just a complete fantasy. And as Warren and I were talking, I guess Mary Shelley, she was a visionary, right? Well, we call her an energy visionary, right? Because she's writing about capacitors, and they haven't been invented yet, right? Okay, that's pretty good. She should have patented it, though. All right, and so, but this actually happened literally years later. Literally years later after she wrote that book. Isn't that cool, right? So this is Ewald, Georg. We have a professor named Georg in our department. That's how I know how to say that word. Von Kleist, and so, and he is credited with making the very first capacitor. Capacitors are pretty simple devices. I keep saying that. I'm trying to convince myself that they are, because the Leyden jar was the very first one, and we have a few Leyden jars here. The Leyden jar is a very, very simple device, and a very dangerous one as well, where you have a metal. Can you see that? Hey, where's the camera guy? Are you there? Can you see the Leyden jar? Okay. So it has a metal outside. It's just like copper shielding. And it's got aluminum foil on the inside. And this is glass in the middle here. And what they usually would do is attach some kind of voltage, high voltage. I guess in the 1700s, it would be some kind of crank voltage. And this is a chain, a metal chain. And so Georg used water. He thought the water was acting as the dielectric, but we know now it was the actual glass that's the dielectric, okay? The glass in between. And then the Leyden jars are many different kinds you can make. Here's another one. This is a metal shield, and then the glass, and then the top of here. Here's another one. Okay, so you can make a Leyden jar. Extremely dangerous, fatal, lethal devices, right? Obviously, because this is not approved by the safety committee at the University of Michigan. Okay, but Warren can do it because he's a professional. Okay, but okay, so this is an old device. And it's storing electrostatic charges in this fluid. You put water in there and it stores the charges in the fluid. But things did change. I'm actually a chemistry professor first. I'm in applied physics and so on. But I guess Michael Faraday is considered a chemist, and so he did so many great things. I mean, if you ever have an opportunity to go to England and see this library and museum devoted to Michael Faraday, he's amazing. You must know that, right? An incredible person. And one of the things he got interested in was to actually, this is actually in the museum there, you can see, is a way to measure the capacitance. I think some people call it the condensing ability, right? The capacitance of materials. And he built this simple device. And it has a ball there that inside that cup you can put any kind of dielectric material, and you can measure the capacitance across it. And then up here, of course, you'd apply your voltages and so on. He was so important, look, he has a stamp and, I don't know, is that a $2 bill or something like that named after him. And so he was a very important person. But the reason why I show that is because now you're actually starting to actually measure something called the dielectric. And so these are the most straightforward way to discuss dielectrics. And let's just start really basic. And we have Monica Wood, who's going to demonstrate a lot of these things, because some of these are kind of dangerous and they don't really trust me doing them. So I tried, but it's okay. So we're going to demonstrate this parallel plate capacitor. And so it was really people like Michael Faraday that he changed this kind of really rough idea of what energy storage was about and electrostatic storage to real hard, straightforward mathematical expression. So, by the way, we should write this. So the capacitance This is, in the 1800s called condensing ability. It is related to the dielectric constant times the area, and then some vacuum dielectric constant divided by the thickness, okay? And so this is a parameter of the material. Remember, I told you that Georg von Kleist, he thought the jar actually was the water was the dielectric. He was wrong, right? It was actually the glass, okay? And so here we have two parallel plates. That's what the picture shows. And we just simply want to apply a charge across these parallel plates and then the charges actually will migrate to one side to the other. Try to make that plate as tight as possible, right? Because that's the thickness. Do you see that, the capacitor? And so she's just charging these two plates to begin with, and the voltage goes up. This is a voltage reader that just measures the voltage across the plates. And of course, if I don't have anything in there, we just have air. Air is not the best capacitance material, so the voltages don't have a lot to hold them. But if I use my handy, more sophisticated cardboard, then you can see even cardboard, even wood actually has a dielectric constant, and then the voltage should go down, okay? Let's start simple, right? So that's a simple parallel plate capacitor. You're applying a voltage across two plates, and you put something in that's not an insulator, right? And it's not a conductor. That's the point, okay? If we have an insulator or a conductor, we will either passing completely charges across the plate or never passing them across the plate and not storing any energy as electrostatic field, okay? So that's the parallel plate. We wanted to show that to begin with because that's the simplest idea, and that's why Michael Faraday was so important, okay? And so it really lays out the groundwork. Well, capacitors come in all kinds of different sizes, at this time, people were starting to make larger and larger capacitors because they simply wanted to see how much energy they could store. It became, if you don't have any restrictions on the actual material that you're actually using to store the energy, then why not try to make the biggest one you can make? And that actually is part of the actual technology of that time. And so, for example, here, you can see the capacitors can be extremely large. And that one of the problems that you're going to see is that the weight of capacitors, the technology and the weight of these capacitors became quite large. But it actually, because of the material and the limitations of the material, the capacitors had to be large because what we're going to show you now is that the actual stored energy is not as efficient for some materials than it is for others. For example, inside here, we have a 7.5 microfarad capacitor. I'm going to talk about units for a second in a minute, but let's just talk about this. So this is a good sized capacitor. This is a capacitor that could do some damage to you, right? So probably this is as big as what's in a defibrillator, right? Do you know what that means? That means, if we had a little accident today, she would take these electrodes off and follow you out the room and give you a jolt. So that's obviously a lot of juice, okay? And so what this is starting to say is that look at the size of this. Just look at it, okay? It's big. And it's big, and it can do a lot. And so that's what the game of the game was in the early 1800s, was to actually just be able to produce a lot of juice. For example, in this case, this cannon is going to actually, I'm not going to touch it. Yeah, sorry. I'm trying to do my best to entertain this crowd, but I'm not going to hurt myself. I'm sorry. All right, so this wire across this band here, it's inside this little cavity, okay? And the wire is going to be charged very quickly with this charging capacitor, and it's going to be charged so quickly it's going to vaporize that wire and cause a pressure wave inside there. And then that actually is going to shoot the cannon. And I guess I'll ask the person with the Northwestern shirt to try to catch this, since they beat Nebraska last week, right?
3, 2, 1.
You missed it. Yeah. Okay. All right, very good. Thank you. All right, so capacitors can do a lot. They're very dangerous and they're very powerful. They're not batteries. I'm going to tell you the difference in a second. Okay, so, but look, at that time, people started to use them for a variety of purposes. Large industries such as RCA and other places were starting to make these industrially, okay, for industrial processes. And this is stuff that people probably weren't talking about, but actually the technology. But then something happened. So I'm not going to say the technology up to this point was kind of low level. I'm just going to say that in 1942 things changed. And the reason why they changed is because you needed a different kind of technology. Capacitors really were kind of like go out to your laboratory or go into your garage or something. You probably could make your own capacitor, right? Literally, I'm serious. And so then this changed, where you started to need energy densities that could prevail for longer times, right? And their values were starting to get as large, or maybe even larger than some of the kinds of things that people were using batteries at that time for. Okay. Now the batteries technology is much larger. Okay. So you want to make sure the batteries they have a lot more energy to give, right? The difference is that the capacitors were pulsed and they could give a huge burst of energy quicker, okay? But they didn't have on average, the energies that batteries had. Do you see the difference, okay? And by that time, the battery technology was starting to break apart and then the capacitor technology followed. All of this happened mainly because of wireless radio or radar, okay? So radar really was one of the greatest inventions of all time, okay? Most people already agree with that. And, and the reason why you needed capacitors and devices like this is because you were carrying these kinds of radars over distances and times of days sometimes, right? And you want to pulsing these kinds of things. And the actual power of the radar was important. It is true that technology and industry, as well as our military laboratories or whatever established there were at that time, we're starting to improve capacitors, mainly because of the invention by this guy, Alan Dower Blumling. And so things did change. So how do they change? Well, new capacitors really started to be created. They were mainly made of ceramic type materials. And you could actually, first, let me just show you this here. These are three different types of capacitors up here that Warren has had in his demo laboratory, whereas you can have, these kind of variable capacitors. There's a series of different kinds of capacitors. These are high voltage capacitors. These are different kinds of capacitors made of ceramic and other kinds of materials. Ceramics tends to be the thing that is considered the standard material in a lot of these materials, okay? And they can apply a big punch. They are nothing to be played at home with. And so, for example, this is an example of a capacitor that can be charged, and it can be charged up to about 400 volts, I guess, right? Okay, but she's only going to do it to 200 volts. And it's just going to show you the kinds of energies that are obtained in these kinds of devices that, again, I said they're simple devices. They look harmless. When she takes these electrodes off, it looks like the same device than before she actually charged it, doesn't it, right? And so that's why I said, that's why she told me not to touch anything. And so she's going to show you.
3, 2, 1.
Yeah. So that charge, talk about, talk about that charge. That charge, we actually want that kind of energy now, right? Whereas this is a demo, and maybe people before were just talking about, showing that demo for fun or whatever. We actually need that kind of energy, and I'm going to show you why. Okay? But ceramics such as barium titanate, tantalum oxides, and other materials are kind of were the standards materials that people were making for these capacitors. They have some problems. they have some problems. One of the things is that if you wanted to increasingly miniaturize these materials, there's a problem with that. Another thing is that while they are really good materials for dielectric, they have very large dielectric constants. That's why they're used, okay? While they have really good dielectric constants, they have this problem with the loss, this recharging ability. And so it's well known that these materials have their stability and their rechargeability properties are not good, but because they can apply such a big punch, people are willing to live with them for shorter amounts of time, right? Okay. So if a capacitor only lasts 1 year as opposed to 4 years, that's fine if it can apply that kind of punch when you really need it. And so, and if you wanted to miniaturize this, you know, these kinds of devices, you can see the capacitors on this PC board. If you wanted to miniaturize things, you're going to have a problem of the heating and so on because of the capacitors. Rechargeability are loss factors. People didn't worry about that too much. So I'm actually now almost up to the present day in history, right? People didn't worry about that because you saw in the Second World War and the Korean War and so on, they still used those kinds of capacitors for radar and munitions and so on. And so it just happened when we started to come into things where we're trying to make all electric things, like all electric buses, all electric ships, all electric vehicles, that you actually now start to talk about needing capacitors that not only can apply the punch, but it's not practical to have a gigantic capacitor in the back of your, Toyota or whatever, right? I mean, you want something like this, not something as big as the car itself, right? And so, but maybe it's useful just to mention a few things, like high energy density. The density is related to that, the energy density is related to that dielectric constant, right? And so you can see here, there's this, epsilon v squared. So the epsilon v squared, it tells you that I can get more energy if I have a larger dielectric constant. And then there's another thing called the power density. It's the same. I mean, they both measure how much energy you can store. But power density is a little bit more specific to some of the applications I'm going to talk to you about. So, because it's kind of related in a time manner. So if you can apply that punch on a faster response time, power density might be better for you. And you can see, for example, the electric bus would be more, you would be more interested in the actual energy density. You just want to know how much. And the bus is moving slow, and it doesn't matter, right? And you actually have to stop and go. It doesn't matter, right? So it's not like you're out on the highway and you can just step on the gas, right? The bus is just it's moving along slow, so it's not a big deal. But look what it needs. It needs about 1,000 to 2,000 kilowatt hours for a daily use if the bus went 500 to 600 miles a day or something like that, all day, okay? Hybrid car is only about 10 kilowatt hours. So you should think about it, almost 2 orders of magnitude different, right? Okay, between the bus and the small car, right? And then the cell phone is just a few watt hours, even more orders of magnitude difference. Of course, if you're a teenager, I mean, that number could be much larger. But I would say even in our, for an average person, it's never going to be even a kilowatt hour. So you can see those are the basic ranges. You would like to be able to lower the size for all of these. That's the key. Okay, keep those numbers. This is what they need. You're not going to change that. They need this. The car needs that. The cell phone needs that. But you could lower the size. Okay, and that would make you a more efficient energy storage device. Okay, and so that has become the game, and that's the difference between Georg and Mary Shelley and what we do today. Okay, is that they discovered those things. But now we need the hard problem of finding efficient energy storage devices. For example, this device here can actually, is a good example. It's actually 3 of these in one device, okay? It's a really good example because it has about the same energy as what I'm going to show you later in the talk. And I just want you to see the size. Unfortunately, it's over there. I wonder if the camera guy, are you seeing that over there? It's big, okay? And it's so big that they call this the killer capacitor. I think it means it's big, not that the instructor gets killed during the demonstration. It has killed 2 people?
No, almost.
Oh, okay. Yes. So anyways, before you start, you apply a high voltage to these very large in-series capacitors, 3 of these. Yeah, I think you're probably, and the voltage causes a large current, which is a magnetic field that's in the perpendicular to the direction of this, right? And the first demonstration shows you that if we put one of these metal plates on top of here, the current in the magnetic field is so strong, it actually will make this metal plate pop, okay? And so she's charging these 3 large capacitors. You should be intimidated by this, right? If you were to see this in your basement, you would probably not touch it, right? Well, and that's related to my punchline, okay? And you're gonna like it. All right, so go ahead.
7. That's 8 kilovolts.
3, 2, 1.
Oh, sorry, I missed it. Yeah. But anyways, it shows you that there's some force. And you're going to see how the magnetic force, this current, actually can be utilized later. That's just showing you that there's these are real properties, right? And can we control them somehow? You know, at first, the simple device, Georg's simple device, was just trying to store voltage and charge, right? Later, now we're talking about, you know, making huge currents, and then from the magnetic field, you can actually, you know, do things, have a force, right? And then, can we actually utilize this somehow? And then here's another demonstration. Can it actually do something? And so here's a can in the middle of that coil, right? And it's just a simple 4-turn coil. There's a magnetic field. So the magnetic field is in a direction that's perpendicular to the current. There's a huge current because she's got 4,000 volts, right? And so can there actually be something that can be done? Can you do something with this kind of energy? It's real energy. I guess that's my point, okay? This is real energy.
So now we're charging up to 10.5 kilovolts.
Okay, so now she's going to 10.5 kilovolts. Again, you need those kinds of large, I changed the slide, but again, you saw the different, the big electric bus. This is electric bus kind of stuff, right? And then you have your smaller things like the cell phone. You would never need this kind of capacitor.
You guys are going to want to plug your ears. Oh, good. All right. In 3, 2, 1.
So, besides this being a very interesting demonstration, it says that, you know, this energy can do something. So that was to show that those kinds of capacitors have the energy that we need, but the size and the scale is not what we want for our applications today. So this is what's really needed. You don't want tonnage of capacitor material. You want a small capacitor. You want something that's thermally stable. It has a large breakdown voltage. That means that it won't, that's kind of connected to the dielectric loss. That means that it won't fail on you. It won't fail on you, right? And so these are the things that are needed. This is, this is where the story, I tell you how we get into this field. As I was saying before, we're doing ultra-fast spectroscopy on organic materials, and these organic materials could harvest the photons, and we would study using the lasers where the photons were going inside the molecule and measuring the energy transfer, okay? And that's what this picture is showing, is that we do a lot of laser spectroscopy on these kinds of molecules and then study their energy transfer processes. It was then that Meng Guo, she's a graduate student in chemistry at the time. This is now about, 7 or 8 years ago, okay? And also Shinzong Yan was a postdoc in the group at that time. And we were working on another type of material that could harvest photons and transfer the energy. But we had made a measurement that showed that the material had an interesting polarization property. Polarization is related to the dielectric constant, that K there. And we thought, well, I wonder if this material has an unusual dielectric material effect. And so, and the reason why this would be unusual is the following. So I told you that in the beginning, Georg used a piece of glass. We used a piece of cardboard. Later, people used ceramics, right? Most people didn't think about using organic materials is because their dielectric constants are always generally very small, okay? Typical, I mean, if you had to guess on any typical organic material, its dielectric constant would be about 3 or 4, okay? And if you guessed on a ceramic material like the one in that killer capacitor, its dielectric constant could be like, 20 or 30, okay? And so that actually has a profound effect on the amount of energy you can store. When we were measuring these organic materials, we were getting much larger dielectric constants in an organic material. That's unheard of. And that was the interesting discovery, is that in one material, you can have a dielectric constant that's on the order of 30 or 40, which I'm going to show you in a second. And at the same time, it has all the good properties that an organic material has that the ceramic materials didn't. Like the ceramic materials suffered from, and it still suffers from these kinds of loss properties, that the recharging ability is not so good. The actual thermal stability of some of these materials is not as good as some of the other materials that they would like to use. And so organic materials didn't have any of those problems, but it had a crappy dielectric constant. And so when Dr. Guo had done these first measurements, this was in 2006, and then this was later patented, you can see this was unheard of. So this is an all-organic dielectric material that has a dielectric constant, and out in the megahertz regime, that's on the order or bigger than 40 at least, okay? And that was a big deal. And like I said, we were doing ultra-fast spectroscopy and so on, and we weren't actually thinking about these kinds of things. We published this result, and then we got contacted by a person at the Naval Research, and just keep that for a second there, at the Naval Research Laboratory. And he had seen this work, and he thought that was really interesting, because they were about making new energy storage devices, but they knew that their storage devices suffered from those problems I was just telling you about. And they were saying, well, how does an organic material have such a large dielectric constant? And so that's a perfect question from a scientific research laboratory like what we have, and we started to investigate those effects. So mainly we started to look into, and subsequently he started a program at ONR on organic dielectric constants. And so that's how that program started. And we give a lot of credit to Meng Guo and Xinxing Zhang for that discovery. But the reason why I think there was a lot of interest in there is that, for example, these people were already trying to do something in this area, but not very successfully. For example, I'm sorry you can't read that first one. It says polystyrene. You can metallize polystyrene. You know what polystyrene is? And you can take a piece of polystyrene and you can metallize it and make a capacitor out of it. General Atomics and other places do that. They actually make simple polymers that cost nothing. Polymers that are so cheap that you literally pay for just the transportation from Malaysia. Okay, that's not a joke. And so can you imagine then, if I only have to metallize it, then I have a real device that costs literally almost nothing, right? And it's not manufactured here in the United States. If you could manufacture it here, then you really wouldn't have to pay anything. And then, but look, its dielectric constant is really small. It's 2.5, you can't read that. But it's got good loss properties. Like I told you, the organic materials had that quality. The aluminum electrolyte is something that's not considered an all-organic capacitor. It is in the present internal defibrillators, okay? If you have such a device, it's nothing more than a capacitor. And the capacitor material, the dielectric material, is made of this so-called aluminum electrolyte. And it's a very interesting market for that. And its dielectric constant is about 7, and its loss is extremely large, which is very troubling. Okay, isn't that interesting, right? Okay. And these are not my results, these are known results, right? All right, and then barium titanate is the gold standard. So if you wanted to make a business, you would maybe stick with barium titanate, at the start, right? Because everybody else is doing it, right? And then it has these values of about 10.5 and 5. And so this new material that we started to investigate had this enormous dielectric constant, is very tiny dielectric loss, and then its breakdown voltage was okay, and it's very thermally stable. So people were very interested in this. But how can it be used? So there's 2 ways to think about this. So I think Myron knows a lot about batteries, and so he kind of was asking about what's the distinction between this and batteries, right? So, for example, these ultra caps, the best batteries are still way superior to capacitors. Okay, the capacitors that we're making now are much better than the batteries of yesterday. But the best batteries today are way better than the capacitors of today, okay? In fact, probably the very best capacitor is only about 20% of the lithium-ion battery, okay? Which is still an enormous amount of energy stored, right? But it's not that. You're not making batteries, right? You're making storage devices to be released, okay? And that means that you should think about their application in terms of the couple of miles of charge, right? And so, but there's another way to think about this, and it's here in the bottom, is that the best battery and the best capacitor can make them extremely efficient device, right? Because if you have a really, really good battery and a very, very efficient capacitor, then you don't need to recharge that battery so many times, do you? Okay? And so this is now the strategy of a lot of the applications I'm going to talk to you about. We're not using the capacitors solo. They're used in parallel with the battery. Okay. All right. So we were successful in doing a lot of really good experiments. It became clear to everybody that this material we were working with a few of the Naval Research Laboratory people and some other people, and it became clear that this was a real finding, this material. And so they encouraged us to start this venture of a small business. So the company's name was Wolverine Energy Solutions and Technologies, or WEST, which is quite a good name, which was made up by Stephanie Goodson, my wife, and I think it imparts a lot of what we're trying to look at. We're actually trying to look at solutions of technology of energy storage, and so I mean, this is not an advertising for the departure of Pfizer, but everybody probably knows that picture is Pfizer. And the university bought that space, and we moved into there. We moved this business in there. Okay, and so it's a nice laboratory space. So I'm in the chemistry. I would say I'm in the chemistry department. It's just right around North University there, and I would say that one of the chemistry buildings that Pfizer left, is state of the art. Okay, and so these facilities are amazing. So what are we doing here? Okay, so. Let's go back to this, slide again, or to go to this slide. There's some opportunities here that you can think about, and you can see that this is power density and energy density. Remember, the power is the pulsed idea, and the energy is the slow idea. So look up there at the top left corner, is that one day somebody will make a capacitor that's the slow type that is just as good as the battery itself, right? That's what so that means that the energy density and the power density, the energy density is so high that for one shot, it looks like a battery, right? Okay? And we're not in that area of research, but there are some people who are trying to do that. And these ultra capacitor technology and so on, fuel cells and double layered capacitors. But then as you move to the right, there's a lot more happening. The aluminum electrolytic capacitors for defibrillators, the capacitors for some of the other things I'm going to talk about, they're generally kind of in the middle to right of this slide. High peak power density, energy density, good energy density, right? Good. I mean, not horrible, but good. And so, and the speed is matter. You can see there's seconds there, okay? So what are we trying to do? So one of the things we've been working on, and this is what this program started, was a project to actually produce capacitors that would store amounts of energy, large amounts of energy, for particular applications. One of them, the applications at the Naval Research Laboratory and the Office of Naval Research is interested in something called the railgun. The railgun is a simple, again, a device of actually firing a smokeless, if you will, a projectile, right? You don't use gunpowder, right? And so you're actually using the magnetic field, very similar to what we were just doing when we busted that can. We have two rails here, and there's a magnetic field that's the B, right? And you can see there's a huge voltage, a huge current that goes across those two rails, okay? And then you can see the driving current. It's in orange in this picture. And then perpendicular to that. So that's a nice little vector diagram there. You can see the magnetic field, the huge current. You could have done the same thing with that example there. And the force popped that ring up in the air, right? Same thing happens here, but this projectile claimed to be at speeds faster than 5 times the speed of sound, right? Okay. And that they want to get 10 megajoules of energy, 10 megajoules of energy are needed to fire such a thing. So Warren and Monica have this small, we don't have such a weapon here, sorry. Okay. They have this small demonstration. And so, again, very, very straightforward ideas. In this case, the magnets actually are sitting right here in the middle of this rail. And the idea here is that you're using the dielectric, the capacitor and the magnetic field to actually do something for you. And so there's no noise in this one, sorry. It's just showing you that, look, you can move this down this rail, and you can see how it's like a projectile, okay? This is a small demonstration what they're showing, and the idea is that the rail has this magnetic field that's passed between it, and a current. These are at immense voltages. A current exists, and the current actually can do work for you. It can do work. Actually, this has nothing to do with the capacitor. This has everything to do with the actual amounts of capacitance stored energy needed to fire this weapon once. Okay, and so they're not going to get it. They're not going to get it done with perhaps capacitors that were used in those days. Look at the series of capacitors that BAE Systems and General Atomics have made to fire that. Those are all capacitors. Okay, and so that's huge, right? Okay, and you can see they fired this once, and then I guess we can do this. The prototype looks like that, and then of course, just last year. Let me see if I can play this for you.
Right now, scientists and engineers are working diligently around the clock to develop a gun for the Navy that can fire a projectile at nearly Mach 8. That's right, almost 8 times the speed of sound. Dahlgren in Virginia is home to the Navy's 8 megajoule electromagnetic railgun. By the end of 2007, the Navy plans to start working with a prototype that is 4 times more powerful.
3, 2, 1, fire.
The high voltage is created by charging up a bank of capacitors. Tom Boucher is test director.
This is our single shotgun. This is our current railgun that we use. It's rated up to 8 megajoules of capacity. There's an upper and a lower rails fully contained within this steel containment. We actually have 220 of these 500,000-pound rated bolts, and they've been pre-stressed to hold everything together. Yet we can put enough current through this that if we don't carefully manage it, it would still come apart. We have huge amounts of forces we're dealing with here.
When the bank of capacitors discharge, a surge of current creates a massive magnetic field. This accelerates the metal projectile to mind-bending speeds. The Navy's goal is to develop a 64 megajoule electromagnetic railgun by 2016. That's 8 times more powerful than this prototype, reaching projectile speeds up to 5,000 miles an hour.
Basically, one ship offshore will be able to cover an arc of essentially 400 nautical miles in diameter. So you could essentially have the Special Forces guys on one side of the battlefield and a major operation on another side, and we'll be able to cover all those with one gun, one ship.
Another application, of course, is these so-called unmanned aerial vehicles, in which you need capacitors that can last longer, that are very thermally stable. These things have already been tested. Again, weight and size is extremely important. And so they won't get it done with ceramic capacitors. And so they're really interested in organic capacitors or any other kind of capacitors that can help solve that weight problem. So you can see the whole payload weight is 2,000 pounds. If that's what you're actually trying to deliver, you can imagine if you have a ton of capacitors, then that's not going to be so useful. You would like to have something much lighter than that on your payload. So we've been working on these kinds of things, coming up with power systems to do these kinds of effects. It's a long call from doing ultra-fast spectroscopy, but to use these kinds of capacitors in conjunction with batteries is the way to go. And the size is orders of magnitude smaller. Interestingly, the market for capacitors in the United States is really dominated by 3 main industries. And some of these industries were just getting started after the Second World War. Some weren't even around, okay? For example, General Electric and other places were getting started, but this Cooper Industries and ABB Incorporated, those two combined make up of about, 65% of the United States market in energy storage capacitors. It's pretty impressive. And so the reason why is because I think people were interested in manufacturing things at very large volume. And so manufacturing things at large volume requires having the facility to do that kind of high toll manufacturing, which a lot of people cannot compete with. And just only recently, when I say recently, the last 10 to 20 years, that it become possible to do that in other countries, right? And so that's the reason why. So, all right, and this is something that we've been working on. One of the things, just as a side note, in doing this is that we got engaged with the Ross School of Business and their School of Entrepreneurship. Meng Guo, who had already been interested in that, took some courses in that, and then we met up with the director of the School of Entrepreneurship, who put us in contact with a professor who was teaching a course on how to start a business to MBA students, and then we made a pitch to these MBA students, and they used our company as their semester project to write a business plan and so on. So I wasn't just looking for a cheap way to write a business plan, but I was also looking for a way to actually learn something, and which I did. And working through the Ross School of Business, they've been really helpful to us. So let's go back to this slide just one last second, since our time's about up. Again, so we're talking energy storage devices I made the distinction because that we have light harvesting, energy harvesting. That's one part of it. It's still extremely important, still very valuable part of the whole energy process. But the storage itself is also apparently interesting and useful as well. Okay, there's a distinction between the two. And while in impact, it may need to compete with nuclear and other things like that, the actual storage of energy seems to be a good investment from an economic, from a scientific, and maybe even from a military aspect. We should remember that in going back to Mary Shelley and other people, we're actually talking about these materials that are in this were discovered by Meng Guo and Xinzong Yang. What is this? I'm supposed to pick DOC. I don't know if you guys can see that. Can you see that? Here's an example of what some of these look like. I don't know if you can see that. See, this is tiny. This is the punchline. And I'll keep the whole politics slide up there too, right? The punchline is that the amount of energy that was in that capacitor, the big one there, and the amount of energy that's in the railgun, we want to replace with these tiny materials, okay? Organic materials. Not this tiny as this little piece of slide, demo slide, but orders of magnitude smaller in size. Orders of magnitude smaller in weight. Their dielectric constants are orders of magnitude larger, so why not? If it works out. And they're also thermally stable. So this is the group, my research group. We're also doing a lot of basic research to understand the properties. This is Meng Guo, who's in the other room. This is Dr. Varnowski, who's a senior scientist. He's been working on a lot of the actual device physics about these work and trying to understand how these materials can be used for specific devices. There's a lot of geometry and engineering that goes into the building devices for these materials. And then Stephanie Goodson, who, as I said, is my wife, who is the president of the company, as well as been working on some of the medical applications, or the future medical applications of these materials. And then I really wanted to thank, again, Monica Wood and Warren Smith for their help on this.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.